Welcome to the continued dialogue about solving linear and nonlinear inequalities. And in this video, we're going to tackle absolute value inequalities. How do you solve those? Now, there is more than one way to solve absolute value inequalities. So there is an easy way and a way that's a little more challenging. And the way that's a little more challenging is actually the same way that we just tackled polynomial inequalities. So that's how we're going to do it, to just continue that process. If there's time and I have the opportunity, I'll make a video of how to do it the easier way. But just to avoid some confusion, this will continue in the same process as solving polynomial inequalities. So same steps apply. The only thing that's going to be different is we have an absolute value inequality instead of a polynomial inequality. So we will go through the same set of steps. If I'm looking at this absolute value inequality, -3 times the absolute value of x plus 7 is greater than or equal to -27. First thing I want to do is rewrite this and revise it so that we're relating it to 0. So move that -27 to one side of the inequality. Okay, so we've moved it, we've added it to both sides. -3 times the absolute value of x plus 7 plus 27 is greater than or equal to 0. So now we want to write the corresponding absolute value equation and take the steps we know to solve that for x. Okay, so remember that when we're solving absolute value equations, we want to isolate the absolute value expression. So this will be a two-step process, which we're going to do in kind of one. First, we're going to subtract the 27 to the right. So we'll have a -27, and then we're going to divide out the -3. So we will end up with the absolute value of x plus 7 is equal to 9. Now, when we do that, remember that we've isolated the absolute value expression. We now write this as two different equations without the absolute value bars, where the constant is both plus and minus. So we have the equation x plus 7 is equal to -9 and x plus 7 is equal to 9. When we solve those for x, we get the values x is equal to -16 and x is equal to 2. So we're going to go ahead and place those on the number line and use them as our boundary points. All right, and then identify the intervals that correspond with this number line that's been divided up. And so remember that we have a greater than or equal sign here, so we're going to need to use brackets everywhere that does not involve infinity. So -infinity to -16, -16 to +2, and 2 to infinity. All right. So, do you remember what the next step is? We need to choose some test values. Okay, so let's choose a value in each of these intervals. Anything in this interval from -infinity to -16, anything in this interval from -16 to 2, and anything in this interval from 2 to infinity. So I chose -20 in this first one, 0 in the second one, and 5 in the last one. And then remember that we're going to use those test intervals in our function, f of x. And I didn't use p of x here any longer because it's not a polynomial function. Okay, and our f of x is -3 times the absolute value of x plus 7 plus 27. So if I evaluate each of those test values, I get these outputs. F of -20 is -12, f of 0 is 6, and f of 5 is equal to -9. Okay, so let's go ahead and then check the outputs of the test values to see if they satisfy this new absolute value inequality. So I'm checking this output, negative 12. Is negative 12 greater than 0? And the answer here is definitely no. Negative 12 is not greater than or equal to 0. Is 6 greater than or equal to 0? Yes, it is. And is negative 9 greater than or equal to 0? And that is a sad no as well. So we can get rid of these two test values. These outputs don't work, which tells me that the only interval that does work is right there in the middle. Okay, so this interval right here, negative 16 to 2, with those endpoints included, will actually work. Now, like I did before, I wanted to show you what this looks like on the graph. If we look at our original graph, if we look at our original inequality, what you see here, this upside down V shape, is negative 3 times the absolute value of x plus 7. And we want to know where is this function greater than or equal to negative 27. So what is the domain? Here's negative 27, by the way. What is the domain of the absolute value graph that's in the shaded region? Okay, because the shaded region is everything that's greater than negative 27. And you can see that that is from negative 16 to positive 2. Now, if I were to use that revised inequality, again, it's easier to see, right? Because I can just see where the x-intercepts are. And what I'm really looking for is where is this absolute value graph above the x-axis. And we can say that that is from negative 16 to 2 as well. All right, so let's do another example. Here our example is 15 is less than 6 plus the absolute value of 4x plus 7. Now, many of you don't like to have the constant on that left-hand side. And I'm right there with you. I would prefer having the constant on the right. So the first thing I'm going to do is move the constant to the right. But when I do that, I want to make sure that I adjust the inequality so that it is appropriate. Remember that 15 is less than the rest of the inequality. So if I move it to the right, I still want it to be the lesser. So I want that inequality symbol to be pointing to the 15, no matter if it's on the left or if it's on the right. So now I can go ahead and work through this inequality, okay? So let's move that 15 to the left of the inequality symbol so that we're relating the inequality to 0. Okay, so I've got 6 plus the absolute value of 4x plus 7 minus 15 is greater than 0. All right, and now I want to go ahead and solve the corresponding equation. So I'm going to set that up as an equation and isolate the absolute value expression. So really, I'm just taking these constants and shifting them to the right. So if I'm looking at the constants combined on the left side, I've got 6 minus 15, which is negative 9. But if I shift it to the right, it will be positive 9. So I have the absolute value of 4x plus 7 is equal to 9. Now I've got that absolute value equation, so the absolute value piece is isolated. Rewrite it so there's no absolute value bars with a negative and positive 9. And then solve for x. Subtract the 7 and divide out the 4. So if I subtract 7 in the left equation, I've got negative 16 divided by 4 is negative 4. And on the right, if I subtract 7, I have 2 divided by 4, which is 2/4 or 1/2. Place those values as boundary points on our number line. And then let's name the intervals, right? Will we use brackets here or parentheses? If you answer parentheses, you are correct. And we have our intervals of negative infinity to negative 4, -4 to 1/2, and 1/2 to infinity, and all of these would have parentheses on them. All right, so our next step then would be to choose some test values within each of those three intervals. So let's choose something in the interval of -infinity to -4, -4 to 1/2, and 1/2 to infinity. And just because I want to be consistent, I'm going to use my 5s there again. I can use -5 in that first interval, +5 in the last interval, and 0 is always a good choice when you can use it. Let's test those values and evaluate f of x in each of them. And our function is 6 plus the absolute value of 4x plus 7 minus 15. And if I evaluate f of -5, f of 0, and f of +5, I get outputs of 4, -2, and 18. Now, when I look at the outputs of those test values, I want to check those against my revised inequality. So I want to see which of those outputs are indeed greater than or equal to 0. And my first one is. My second one, -2, is not greater than or equal to 0, but my third one is as well. So I can eliminate that middle interval as not a part of my solution set. The two outer intervals will be my solution set. So looking at this graph, you will see that everything above 15 is shaded. Everything that is greater than 15, okay, greater than the 15, that's shaded purple. And this green graph represents the graph of y equals 6 plus the absolute value of 4x plus 7. So what we're looking for here is, what is the domain of the green function that lies in the shaded region? And we can see that that is everything from -infinity to -4, and then again from 1/2 all the way to +infinity. So now, as we're looking at the revised inequality, remember that we are looking at how does this relate to the x-axis, because we want to know where is it greater than 0. And we can see that the graph is in that shaded region, which is above 0, from -infinity to -4, and also from 1/2 to infinity. That wraps up absolute value inequalities. Our final type of inequalities we're going to look at will be rational inequalities. I'll see you there.